Thank you for joining our discussion, Craig.
Great to be here. Typically, the issue with conducting field experiments in the fire environment, you're pretty much at the mercy of the fire manager. So if they're going to do a prescribed fire and you want to do the research, they're going to say, hey, we're going to burn it like this because that's our prescription. You can set
Yeah,
your stuff up any way you want, but this is how it's going to go down. In the case of the canyon, we planned this a year ahead and said, hey, we want to do a head fire in a canyon that's quite steep where there's really no control. And so it turned out that they had this big prescribed fire project on private land where they were able to burn out about a mile behind the canyon a couple days before and then left the canyon to do this experiment where we were just a simple ignition and just let it go. Usually they'll use helicopters and it's, igniting it all over. And it's really difficult as a modeler to try to simulate that. You want a very simple ignition. So you know your ignition is right, and that way you can see how it evolves and if the model got the fire behavior right. But if you don't get the ignition the way it was ignited in real life, then your model's never going to be able to get it right, or you're never going to know if it's right. So it's really important to have the ignition timing and the ignition type down. So a line ignition or with a walking drip torch is really, pretty easy. You just, ideally you just want it to have a line just instantaneously ignite across 100 meters. As I mentioned before, we run a modeling framework that's a forecast system. And once that fire kind of broke out, it was like, hey, are we running this? Are we running this case? Because this is a big one. And so they started it like late the next morning, but forecasted it for the next, 48 hours, or actually even like four days out, because the fires keep burning. But the most critical part is just like the initial few hours, right? And so the team at San Jose State has collaborators at another university, University of Colorado, Denver, and at they actually run it automatically. So there's a fire detection by satellite. The model spins up automatically, runs it from that ignition point, and so it's a forecast. Even before you even know there's a fire, the model had already run. Now the model is slow because it's a computational fluid dynamics model linked with a combustion type of model and an air chemistry model. So all these codes are running on a supercomputer that we have at San Jose State, and the output comes like every 4 hours. So there's more simple models that a lot of agencies run, and there's a lot of tech companies that are running these simple models. They can actually forecast it in just a minute or two, and different variations of the simulation. So you can model, oh, what if the fuel moisture is a little bit higher? What if it's a little bit lower? What if the wind's a little bit higher, a little bit lower, different direction? They run all these scenarios and they can run it much faster, but it's not at the resolution in the as our model, and it doesn't have all the physics. So there's a trade-off: slower but more accurate, scientifically sound, physics-based coupled fire atmosphere model, or a simple 2D model that you can basically run on your phone, but a little more sophisticated, using also HPC or high performance computing systems. And so we've been really pushing from our center and from our standpoint that you really have to take into consideration the atmosphere. You have to model the coupling between the atmosphere and the fire, because without it, you can't get the spread rates correctly. And that's been proven in literature. Like you uncouple, if you run a fire simulation on a simple grass fire, and if you don't take in consideration the atmospheric coupling, you can't get it right. And well, I don't have it here, but there's lots of examples where different direction winds, wind shear is where you have winds going from the opposite directions in the vertical, that causes turbulence. And when you have wind shear in a fire environment, the fire does completely different things. And a 2D model cannot simulate the wind shear because it doesn't have the third dimension of the vertical. And so you can miss out a lot of extreme fire behavior by not including a 3D coupled fire atmosphere model simulation of a fire. So I know I'm getting into the weeds a little bit about that, but those downslope windstorms, they have that third component because they have a vertical profile of the atmosphere that's, associated with the downslope windstorm itself, and that can help drive extreme fire behavior. In addition to the canyons and all the terrain, and it's a complex environmental system. And, as a meteorologist, I always think, tornadoes, we still can't forecast tornadoes. We still don't really know the origin of tornadoes and, as well as we should. But when we're trying to forecast, severe weather, we kind of understand that. When we think about fires, it's so complicated because terrain, fuels, houses, communities, and the weather, they all play a role, and they all can change the dynamic of that fire behavior in each individual case.